now go to the presentations of the companies, and we are really happy to have with us several of the world-leading companies, and we start probably with the world's largest vertically integrated company, world's largest wafer manufacturer, world's largest module manufacturer. So we're really happy to have with us Jason Yan, who's the Senior Product Marketing Manager at LONGi Solar, and he will provide an overview on the optimal module size from LONGi's view and how they implemented advanced soldering technology into their products. Jason, the floor is yours.
Hello, Michael. Thanks for your kind introduction. So, hello, everyone. This is Jason Yan. I'm very honored to give a speech here, representing from LONGi. So I think I will share my screen now. So today my topic is about the insight on optimal module size and advanced smart soldering technology. Basically, my presentation will include 3 parts. So the first part is about a review on the technology innovation, and second one is about the insight on the optimal module size for the utility scale power plants, so which includes the shipment feasibility, manual handling feasibility analysis, and also the model reliability and the BOS cost analysis. So last but most important, I will introduce the advantage of HAMR 5 model based on 182 millimeter with smart soldering technology, also including the better reliability, higher efficiency, and some application cases. So firstly, as we all know, the first principle for advanced product and the innovation is based on always the better LCOE and reliability. So models are built and power plants are built to last 25 30 years or even longer. So the models performing well against the extreme weather conditions become a necessity. So the core of reducing the LCOE is to comprehensively consider the I think the model cost, the BOS cost of the power plants, and also we need to consider the stability of the energy yield and the reliability of the whole system. So when we review the history development of the industry, we can see we can work on these 3 aspects, including silicon wafer and cell and the model levels to achieve the better LCOE. So basically, in terms of the wafer size, so we can see as the figure for last 10 years by the technology innovation on the process of crystal growth and the diamond slicing technology, the cost of the wafer reduced about 80%. And also the content of oxygen and the content of carbon and metal impurities is significantly reduced. So that will help us get the high quality wafer and also the high efficiency cell. This is very helpful for deliver high value to our customer. And also, I think in 2019, LONGi adopted the gallium-doped silicon wafer for all of our products. So actually, we overcome the technical challenges such as large segment coefficient, so able to reduce the cost and deliver the same price as the boron-doped wafer. Basically, the advantage of the gallium-doped silicon wafer is to actually we can have a better LID and the LETID performance as shown in the left-hand side data. And also, it can increase the cell efficiency about 0.09%. So with all of these advantage, we can ensure the value of the customer power station throughout the full lifetime. And also in terms of cell, I think it's cell technology and the model level. I think in 2017, so LONGi promoted the bifacial model and establishing the bifacial model backability all over the world. And we can see in the figure, we beat a lot of pilot projects with third-party lamps. So with all of this data, we convinced our customer to accept the bifacial model because the advantage of bifacial model is we can utilize the backside ingredients and get more power. However, I think the price is the same. So, and also bifacial model is more reliable because it is used double glass structure. So once it is released, the bifacial model is well recognized and accepted by our global customer. I think until now, the market share of bifacial model is around 30% to 40% of all the models. I believe in future years, the market share of bifacial model will go up still very quickly, maybe over 50% or even bigger. So also in terms of the 106 model level, when we look at the launch of the 166 standard model, basically in response to the mixture application of multiple wafer size after 2018, LONGi advocates the standardization of M6 standard. The length and the width of the 160 model are slightly increased by 4 to 5%, which can realize the full scenario replacement of the original product. And besides, the appropriate increase of the model will reduce the labor cost and the cost of mounting system and pipe foundation. And also, since the M6 product utilize the equipment margin for the cell production, and it is compatible with the existing, I think it's 200 gigawatts per cell capacity. So it is well recognized and accepted by the global customer, and the cumulative shipment of, I think, 166 model has reached 10 gigawatts per year, and driving the standardization of product specification. I think this year, regarding the 160 model, the market share is about, I think it's 50%. So as I addressed above, all of this technology regarding the cell, wafer, and the models, once it helps reduce the LCOE, it is the technology innovation, and it will be recognized and accepted by our global customer. So for the new product capacity, actually the size of cell and the model can be further enlarged than M6. So we should consider comprehensively different factors enable customer value and help reduce the LCOE. For example, we need to consider not only the cell and the model manufacturing process, and also for the model deployment process, such as model installation and model transportation, and long-term reliability and system compatibility. So next part, I will introduce the insight on the optimal model size for the new capacity for the utility scale power plants. First part, we do analysis on the shipment feasibility. As we know, so landscape package and a double stack of pellets is the best known method for many years, which is mature and reliable. So 182 millimeter wafer size is the maximum size best fit for the 40 high cube ship container. which can be calculated from this equation. We can see in the right-hand side figure picture for the 182 millimeters models, no matter in the loading and shipment and unloading, it's very mature and reliable in the real field test. And normally, if we want to further increase the wafer size to bigger than 182 millimeters, that means we need to change the package method to whether flat ones or portrait one. So both of these package method will increase the risk of micro crack and breakage and the falling. So second, as I mentioned, if we want to increase the wafer size further bigger than 182 millimeter, so that means we need to change the package method to the portrait one, and also we need to anti-falling bracket beside the model to ensure the stability of the models. That means it will have a lot of limitation as I analysis in the right-hand side figure. So for example, because the large counterweight is needed for the anti-falling bracket. So for instance, for example, at least 666 kilogram counterweight is needed if the angle of motor is about 75 degrees C. And also when the wind speed is 10 meters per second and the number of motor is less than 9, and the bracket will be blown down by wind. And also in terms of manual heading feasibility, so normally the motor width is derived from the natural expansion width of the human arms, and too wide of the motor will bring inconvenience to installation, and the too weight of the motor also will cause difficulty to the motor installation. This table shows the different size motor and different weight of data. So we can see for the M6 and M10, the weight of the motor is below than 35 kilograms. And for the G12, if we use the 60 or 66 cells design, that means the motor weight will be bigger than 35 kilograms. That will cause significantly higher difficulty in manual handling and installation. Like in the right-hand side of the figure, it's a real field application case for the oversized model. We can see the human is very difficult to install the models. And after analysis on the transportation, manual handling, so this part is about the model reliability. So as I mentioned above, models and power plants are built to last 25 or 30 years. So their performance against the extreme weather conditions become a necessity, and is to ensure the stability of energy yield and for getting the better LCOE. So actually we did a lot of tests to simulate the the weather conditions, such as the wind, the snow, and the hail impact. So first test is a mechanical load, which simulates the snow condition. We can see for the oversized mode, in which the motor width is bigger than 1.3 meters, it will yield about bigger than 40% higher deformation under the same load, which is 2,400 Pascal. And also the risk for micro crack will increase significantly, as shown in the right-hand side of the figure. We can see oversized model will have, I think, is 7 times micro crack cells than the 182 millimeter model. So basically, using the same 2 millimeter plus 2 millimeter glass construction, motor size cannot continue to increase without compromising reliability. And also, this is test about regarding the wind tunnel test, which simulated the, I think, is wind weather conditions. So basically, we can see this is a short video. Shows this is oversized model. We can see under the speed of 45 meters per second because of the large shear stress in the mounting hole. So the mounting hole is tear down and the motor is blown. However, for the 182 model, we tested the speed increased to 60 meters per second, and it's still very stable and reliable. So the main mechanism is because that if we increase the motor size significantly, that means the shear stress in the fore mounting hole is bigger, which means the stress of the motor is less. And we tested as in the left-hand side of the figure, we tested the average vibration acceleration rate of the oversized motor, which is 300% than the 182 millimeter model, and also the strength of the oversized motor is only, I think, 70% of the 182 model. So all of these material features and motor features will lead to the failure in the or when it faces the extreme weather conditions. And also, this is the hail impact test. We show in the left-hand side of the figure, we did analysis on the surface stress for different waste glass. For example, for the we can see the red curve is about 1.1 millimeter with glass, and a black one is 1.3 meters with glass. So actually, we can see the surface stress of the oversized model is 10% lower than 182 model, which means that the hail impact resistance is weaker. So because of the weaker of the glass, it will lead to the hail impact test failure. So in this, we test the 3 samples and the 35 millimeters hail impact test. So all these 3 oversized model failure on the test. All of these showed the glass breakage in the edge. And also another test simulating the I think outdoor wind is the dynamic loading test. So we want to test the threshold performance of our 182 millimeter wafer model. So we increased the I think the test to 1,500 Pascal, and we can see in the left-hand side figure our HAMR 5 based on 182 millimeter passed after I think 22,000 cycles test, and after the test, the appearance is still intact and perfect, and the EL image shows no micro crack. However, with when we see the public release for the oversized model, it failed after 2,000 cycles. So that means the dynamic mechanical loading lifetime of our HAMR 5 is over 10 times than that of oversized model, and it's mainly affected by the motor size and the frame design. And so because of the optimal motor size of HAMR 5 and the robust frame design, all these factors will contribute to the higher reliability of HAMR 5. So after analysis on the reliability, so last part I will show some analysis on the post-cost savings. So basically 2 reasons why large format model will save the record and the foundation cost is that firstly, when we increase the record length, that will save the number of foundation. For example, if the large format model will only use 5 pile foundation and the small one use the 6, so it will save 1 pile foundation. This is just a typical example. And also the increase of the record width increase the supporting power. for each foundation. However, as for in the real application case, we can see we can optimize the number of strings per record, for example, from 2 strings, 4 strings, and 6 strings to optimize the record cost and pile foundation cost. So after the analysis of the fixed rack, this is for an example of the 1P tracker system. As you can see in the table, due to the limited length of the tracker, so 210 model will reduce the number of strings from 3 to 2 on 1P tracker. So the total, that means the total power carried by single tracker is lower, and the cost per watt is higher. We can see the for the 565 watts and 655 watts model, the total power carried by the rack is about 40 kilowatts, and for the 182 model, the total power is 45. That means the total power is 10% higher than the 210 millimeter model. And also we did an analysis on the BOS cost verified by the DMV, and for 3 different models and for different scenarios. For the scenario 1, 1P tracker, and 2P fixed tilt, and also the 4L fixed tilt. This is the detailed test results. So you can see BOS cost is also the principle is based on the same length of record and installation cost. Of course, from the table, we can see there is slight advantage in 182 model due to the higher efficiency. Actually, from the for the 4L, 2P and 1P tracker, it will save both cost euro cents from, I think it's from 0.2 to maximum 0.6 euro cents per watt. So this mainly, I think, is because the land cost is because the high efficiency, so it will save the land cost, and also in the rack and pile foundation cost. And this is just is an example of the system layout for the scenario 1P tracker system. We can see for the 1P tracker 182 millimeter model, we can see the power plants, the whole power plants will have 84 records, and for the 210 6-cell 1P tracker, it was 98 records. So that means this will have more record cost than a 182 millimeter. This is just a simple example. And last but most importantly, I will show some advantage of HAMR 5 model with the smart soldering technology. So after the thorough analysis, as I mentioned before, regarding the model level, cell manufacturing process, and the model deployment process, including the manual handling and installation and transportation, long-term reliability, and BOS costs. We think the HAMR 5 based on the 182 millimeter wafer is the optimal model size for the utility scale power plants. So HAMR 5 adopted the M10 gallium-doped mono wafer and the smart soldering technology with a reasonable 72 cells model design. This is because my topic is about the smart soldering, so this slide is introduce the smart soldering technology. Basically, the smart soldering technology will reduce the tensile stress of cells about 20%, compared with the flat ribbon and the circular round ribbon, enable higher reliability. And also because of the insight on the optimal size, so LONGi's 182 model won the 2021 Intersolar Award, as shown in the right-hand side figure. This slide is a simple introduction of the smart soldering. So this explains why we choose the smart soldering technology for our HAMR 5. So because we consider the power, efficiency, manufacturing yield, and reliability, we think the smart soldering is the optimal cost-effective technology. We can see in over these 4 figures show different technology. So the first one is the round ribbon. It's normal gap, which is about 2 millimeters gap. So that means it will have more black gap and lower efficiency. And then the industry think to so we can narrow the gap. So the second technology is the round-shaped ribbon, which is called the Taiyang. It can increase the motor efficiency about 0.4% efficiency. But however, because of it will deform during the assembly process, so that means it will have a lower manufacturing yield and a small crack will initiate. And also it will use thicker encapsulation, and it means high cost. And another technology is round-shaped ribbon is small gap. So it's not overlapped. It's also have, I think it's for the industry, different products have a different gap. And normally from 0.5 millimeters to 0.8 millimeters gap. So that means it will increase the motor efficiency about 0.3% higher. Also, but it not solve the small crack problem. So the small cracks will still exist because it will locally flatten during the sintering process. And it's also very difficult for the process control. So the last one is the smart soldering, which is the integrated segment ribbon with a small gap as 0.6 millimeter. And so it will increase the motor efficiency about 0.3%. So basically, this technology actually use a ribbon that which is pre-annealing. That means it is no deformation during the soldering process, and it will I think it will have a higher manufacturing yield and much reliable according to the test. So this slide show the advantage of the smart soldering, which is one is the high power. So this is basically 2 kind of technology. This is round ribbon, and this is the integrated segment ribbon. So this one we can see that when the light is introduced to the surface of the ribbon, some of them will directly goes into the cell, and some of them reflect to the glass and secondary reflect to the cell. That means it will cause some light loss, and glass and UV will absorb some light. And however, for the smart soldering technology, so the light will directly introduce to the cell. That means it will improve the light utilization about 10%. And another advantage is the material features, as I mentioned above. So this is I think is integrated segment ribbon with the smart soldering. We did a test, a small test. It's actually, it will fracture after 20 times 90 degrees C bending. So this is a round-shaped ribbon because it is locally flattened during soldering process. It means the higher internal stress in the intersection part. So it will fracture after 7 times 90-degree bending. And right-hand side figure, also we test the yield stress of the 2 different technology. That means the integrated segment ribbon will have the lower yield stress, which is soft and toughness, and the round deformed ribbon, which is brittle. So that means lower lifetime of the round-shaped ribbon. Another advantage is that a smart soldering is a reliable process. We can see, as I mentioned before, since it is no deformed process before the soldering, so it shows the good process stability, as shown in the left-hand side figure. So the cell gap is uniform and process is stable for smart soldering. However, for the round-shaped ribbon. We can see in the right-hand figure, the first one is the cell gap is not uniform so for this cell, I think is bigger than the gap. This one almost 1 millimeter, and so this one is about 0.4, 0.5, and this shows some round ribbons are not deformed because of the difficulty for the contouring the process. And also we did the reliability test for the compared with smart soldering with the round-shaped ribbon. We can see for the smart soldering under the dynamic and mechanical loading test, which is 1,000 Pascal, 1,000 times the EL before test and the EL after test, which shows no micro crack. However, for the round-shaped ribbon, we can see after the test, the micro crack of the cells increased to 7 cells. So all of this, as I mentioned before, the smart soldering has a high efficiency, high reliable, high power. So HAMO 5 based on the smart soldering model until now, as we published, I think several, I think 1 week before, it has existed 10 gigawatts global shipment all over the world. It's well recognized and accepted by our global customer. Finally, into the conclusion part. So from M2, M6 to M10, including wafer and model size has been an effective approach to increase the model power output and reduce both cost and LCOE. And the size of P model is not always the bigger the better. We think it's necessary to comprehensively consider all aspects of model manufacturing process as well as model deployment process, transportation, installation, and long-term reliability, and to evaluate the associated risk. So 72 cell M10, which is based on the 182 millimeter cell, is the optimal model design for the utility scale power plant after the thorough analysis on the whole value chain. And we think the future efforts to lower LCOE will focus on the model efficiency improvement to reduce the BOS cost and improve the energy yield. That's all. Thanks for attention.
Thanks, Jason. Very nice. Quick question. You said 10 gigawatts recently were shipped. So what's the plan for next year? I think LONGi has 50, 60 gigawatt module capacity. So what's the breakdown for next year that your plans for in terms of shipments for 182 versus you still have 166?
So actually for next year's plan, actually I think our main product is 182 millimeters models. So it will be, I think, is bigger than 50% of our global shipment. And I think another product is also the HAMO 4 model based on 166 millimeter wafer, which is I think is suitable for the utility and it's for rooftop and CNI applications.
Okay. There was also a question on, at the moment you have PERC, but how is your top? You have recently also shown some efficiency improvements for both TOPCon heterojunction. Can you just let us know what's the plans are for these technologies in terms of product releases?
So basically, as you can see, in the last few months, we have updated the efficiency record regarding the TOPCon cell and also for the HJT cells. So as I mentioned, we think the future approach for getting the low LCOE is to increase the efficiency, which will be helpful for deliver high value to our customer. So basically, I think in next year we have we will have more, I think, higher efficiency products still based on the 182 millimeters wafer size model. Yeah.
But still PERC based before, so that's, or will we see products, TOPCon HJT products already in 2022?
Yeah, next year, yeah, it's different. I think it's not the PERC, yeah, different, maybe N-type, yeah.
Okay, okay. What about, what else do we have? There was one question regarding encapsulation, EVA versus PO. Are you continuing to use EVA as encapsulation material, or are there plans to use also other?
Basically, for our bifacial model, we still use the POE encapsulation, which is I think is more reliable and it's better in the PID resistance. So normally for the I think the monofacial model, we use the EVA, still use the EVA. Yeah.
Okay, super. I think we're running a little bit out of time. If you have time, Jason, it would be nice if you could also answer some of the questions in the chat. I think there's a lot.
All right. Okay, no problem. It's my pleasure.
That would be nice.
Yeah.
Okay, super. Thank you. Great presentation. Thank you. Okay. Okay, then let's